Okay, this is a dynamical systems practice final exam. So if you want, you could scroll through this and try all the problems. There's 10 of them if you want. You could pause the video at your convenience. Um, let's get right into it. I'm going to go through all the major steps and explanations. Some of the calculus, algebra, arithmetic, I just skipped through just because of the level of mathematics it's at. And hope this helps you if you're practicing for a final exam in dynamical systems. So, number one, here we have this system. Find all fixed points, compute the Jacobian, classify each point, sketch a rough phase portrait near each fixed point. For this, instead of sketching it, what we're going to do, just going to say describe. So instead of sketch, we're just going to describe near each fixed point. Okay. Fixed points satisfy these equations. So what we're going to do here, set each of these equal to 0. Solving systematically using algebra, first equation, we're going to find out here either x is going to be equal to 0 or 2 minus x minus y equals 0. Okay, so we're setting these equal to 0 first. Second equation, do the same thing, set equal to 0, and we find either y is 0 or 1 minus x minus y equals 0. Okay, what we're going to do from here is we're going to combine the cases. We're going to have 4 cases we're going to test. Case 1, x equals 0, y equals 0, gives an equilibrium of 0, 0. Case 2, x equals 0, y, and 1 minus x minus 1 equals 0. So then 1 minus y equals 0, y equals 1, equilibrium 0, 1. Case 3, y equals 0, 2 minus x minus y equals 0, then 2 minus x equals 0, x equals 2. Equilibrium there is 2, 0. So we have 1, 2, 3 equilibrium points, and then in case 4, we're going to do them all simultaneously. When we do them simultaneously, we're going to get 2 different answers here. X plus y is 2, x plus y is 1. 2 doesn't equal 1, so this is invalidated. That is impossible. Okay? So we get fixed points at 0, 0, 0, 1, 2, 0. Okay? And then we could define f of xy equals x times 2 minus x minus y. G of xy equals y, 1 minus x minus y. Okay? Using algebra, we expand both. I'm just going to write f of xy as f, g of xy as g. We get that just by distribution. Okay, so I'm going to go through this quickly because I expect, well, if you're watching this video that you're taking or you took dynamical systems and you have a strong background in calculus, so I'll go through all that pretty quickly. Here we compute the partial derivatives, x partial, f of x partial, f of y partial, g of x partial, g of y partial. That's what we get. Okay, so now moving along, let's see what we can do. This is letter B, right? Okay, we want to compute that Jacobian matrix. So we have our partial derivatives here for letter B. And let's set up our Jacobian matrix from this. J of xy is 2 minus 2x minus y, negative y, negative x, 1 minus x minus 2y. Remember where your components go for a Jacobian matrix. We're going to evaluate now at the 3 equilibria. Okay, 0, 0, or fixed points rather, we could say. In this situation, technically fixed points. 0, 0, 0, 1, 2, 0. At 0, 0, 2, 0, 0, 1, we get eigenvalues. Lambda sub 1 is 2, lambda sub 2 is 1. Both are positive. So remember in this case, if both of these are positive, then at 0, 0, we have an unstable node. So that's a source. Moving to 0, 1. Evaluating the Jacobian there, 1, -1, 0, -1. Okay. Our characteristic polynomial is 1 minus lambda times -1 minus lambda. Set that equal to 0, and when we solve, we get lambda sub 1 is 1. Lambda sub 2 is -1. They're opposite signs. Opposite signs, in this case, saddle. Okay? And then the third point, 2, 0. -2, -2, 0, -1. Eigenvalues here are diagonal entries, since this is triangular. So lambda sub 1 is -2, lambda sub 2 is -1. Both of these are negative. So if both of these are negative at that point at 2, 0, that's a stable node, and we have a sinc classification. So going back to part C, classify each fixed point, sinc, source, saddle, etc. Here we have our classification, summary, equilibrium points, eigenvalues, and we indicated source, saddle, sinc. In B, we actually did C technically in B, but this is just a chart. Groups them nicely. And now letter D, just going back. Letter D, for this, we're going to describe what happens near each fixed point. Okay, so describing what happens near each fixed point, this is important. So near 0, 0, think about what's happening. Okay, near 0, 0, that's your unstable node, your source. So trajectories in this situation are moving outward. If we go to 0, 1, that's technically one stable direction. We have a saddle there. And we have one unstable direction, saddle, right? And then we have the situation with a sinc at 2, 0. So the sinc near 2, 0, the trajectories, where are they moving? Not outward, they're moving inward. Trajectories moving inward near 2, 0. And that would take care of describing that for letter D. So that is number 1. I'm going to go through this rather quickly because you could, do these problems as you go along, check your work. And also, the steps are there. Let's see here. Moving along. Number 2. There's 10 problems, by the way. So number 2, we consider this. Okay. We have this. This is in Newton's dot notation. Remember, that's dx dt, dy dt. Show that the origin is the only equilibrium. Okay, so 2a, equilibria have to satisfy these conditions, right? Set these equal to 0, and we're going to solve for our variables. Now, what we could do here is just set up a system of equations. Technically, we set these equal to 0, set up the system of equations. Y is x cubed. Substitute that into the second equation, set equal to 0. Algebra here, solve, and think about what happens here. If we set this up as 1 plus x to the 8th is greater than 0 for all real x, x has to be, in this situation, x is 0, and y equals x cubed equals 0. Just doing the algebra here, the only equilibrium is at 0, 0. Okay, and that's just pretty much algebra there for the most part. Now in part 2b, it gets interesting. We want to linearize the system at the origin and classify it. So we define these as functions. We'll call this f of xy, this g of xy, right? Set up our Jacobian matrix. Set up the Jacobian. Take the partials. At 0, 0, plug these in. We get 0, 1, -1, 0. Now in this situation, the characteristic polynomial is lambda squared plus 1 is 0. So we get lambda is plus or minus 1. So this is important to recognize. The linearized system has imaginary eigenvalues. That being said, the linearization is a center. Okay. So, moving forward to letter, that takes care of letter B. Yeah, we're good. Letter C, explain why the linearization is inconclusive if it is. Okay, so here's 2C up here. Since the eigenvalues are purely imaginary, right? What we could say about the equilibrium, it is non-hyperbolic, okay? The linearization only determines stability for hyperbolic equilibria. There's where no eigenvalues with zero real part, okay? So therefore, the linearized system cannot determine whether, keyword cannot, determine whether the nonlinear system is stable or unstable. Okay. All right. Now moving along to letter D. Lyapunov function to determine the stability. So what we're going to use is v of x of y, 1/2 quantity x squared plus y squared. This situation, it's positive definite. Find its derivative along its trajectory. So think about what we have here. Okay, take this v, right? Newton's dot notation equals x. X dot plus y dot. Substitute the system to here, right? Substitute. Rest is mostly algebra, okay? Forming the algebra here. And then v dot is 0 only at x equals y equals 0, okay? So that requires you knowing about Lyapunov. It's not too bad. Now, what can we say from this? We wind up with x equals y equals 0. We could say that therefore the origin is asymptotically stable by Lyapunov's direct method. And technically it's globally asymptotically stable by Lyapunov's function. Okay, so that looks like it takes care of letter number 2. That's A, B, C, D. All right, moving along. Let's take a look at number 3. Number 3, we have an ODE, ordinary differential equation. Okay, so this would be technically dx dt equals x squared minus 4, right? X dot Newton's dot notation. Find all equilibria, determine the stability, solve the ordinary differential equation explicitly, and describe the long-term behavior of the solutions depending on initial conditions. So this one isn't too bad. First, set this equal to 0 because it's already dxt, it's already in derivative form. We could get the equilibria. X equals plus or minus 2. Those are equilibria. From there, we use f of x equals x squared. We take the derivative of that as 2x. Okay? And we're going to substitute our equilibria. At x equals negative 2 in there, negative 4 is less than 0. So what we could say, if it's less than 0 for that derivative, substituting that negative 2 equilibria, okay, x equals negative 2 is asymptotically stable. Less than 0, asymptotically stable. Okay? Now if we substitute the 2, f prime of 2 equals 4, that's greater than 0. Well, if it's greater than 0, at x equals 2, it is unstable. Okay? So part A, we got the equilibria. Part B, determining stability, not that bad. You could go through that. So we're done with A and B. Now part C, okay, we want to solve this ordinary differential equation explicitly, and we're going to use some stuff from Calculus 2, partial fractions, to help integrate that. So remember that Newton's dot notation, this is the same thing as dx dt equals x squared minus 4. Luckily, separation of variables works. Dx over x squared minus 4 dt. And we could write this as x squared minus 4 as x minus 2, x plus 2. That is going to help us with the partial fraction. So we set this up. So this component here we could write it as partial fraction 1 over, this is going to become 1 over x squared minus 4 equals 1/4 the quantity 1 over x minus 2 minus 1 over x plus 2. You could do your A and B. I skipped a step there, but assuming if you're in this class, you definitely had Calc 1, Calc 2, Calc 3, vector calculus, so you've probably done a bunch of partial fraction integration. Okay, integrate here, it's not too bad. We wind up with 1/4 natural log of x minus 2 over x plus 2 equals t plus c. Exponentiate, taking base e, and just solving. Rest is pretty much algebra. We wind up with x of t equals 2 times the quantity 1 plus c e to the 4t over the quantity 1 minus c e to the 4t. Okay, so that's good there. That looked good for, yep, letter C, done. And now the interesting part, describe the long-term behavior of solutions depending on initial conditions. So long-term behavior. Here, from the phase line, so if we go back here on this domain from -2 is less than x is less than 2. Then we know from all this information, x squared minus 4 is less than 0. And what happened in that situation? The solutions, what's happening to them? They're decreasing as they go towards -2, okay? Now from here, what we can do is that x squared minus 4 is greater than 0. What's happening in this situation? If x is less than -2, then x squared minus 4 is greater than 0. So the solutions increase towards -2. Thus, all initial conditions with x naught less than 2 approach x equals -2. Okay, so second component of that, if x naught is greater than, okay, what we can do, x naught greater than 2, then x naught is greater than 0. I'm sorry, x dx dt is greater than 0, right? This would be dx dt is greater than 0. So solutions increase without bounds and blow up in finite time. If x naught equals 2, then the solution stays at 2. So that's a description of this. Okay, so that takes care of the long-term behavior for what we were given. So that's A, B, C, D. That's good for number 3. We're headed to number 4. Okay, so number 4. Okay, we have a dx dt again, Newton's dot notation, equals rx minus x cubed. Similar start, find all equilibria as a function of parameter r. Okay, well, again, set this equal to 0. Okay, we're going to get, looks like 3 equilibria. Solve for 0, x equals 0. And when r is greater than 0, x is equal to plus or minus square root of r. Okay, now we're going to, for part B, determine the stability of the equilibria, similar to the previous problem. Set this f of x, set this as f of x equals to rx minus x cubed. Differentiate with respect to x, we get f prime of x equals r minus 3x squared. We get the equilibrium, x equals 0. Take the derivative of that at 0, f prime of 0 equals r. So what we could say in this situation, think about terms with stability and the rules. Stable if r is less than 0, unstable if r is greater than 0. Okay? So the equilibria where x equals plus or minus square root of r, f prime of plus or minus square root of r, well, we're gonna have that becoming r minus 3r. Okay, and if that's r minus 3r, that's going to wind up at -2r. So if we write this in terms of inequality, for r is greater than 0, -2r less than 0. Okay, and in this situation, what we can say, both are asymptotically stable. Okay? Both are asymptotically stable. Okay. Now, going to letter C, identify and classify the bifurcation. What we could say is at R equals 0, one equilibrium splits into 3 equilibria. And what we would call this is a supercritical pitchfork bifurcation. Okay? Remember, if you, that's what that would be called. And again, this final exam, practice final exam assumes that you've seen all this stuff before, okay? Or hopefully. If not, review it, or try to, if you have time. And letter D, sketch the bifurcation diagram, but this was supposed to, I'm just going to say here, apologize, describe. It's hard to write on here. Whoops. Let me just put this down for a second. Describe. Okay, we're going to describe the bifurcation diagram. So we have a description here. For R is less than 0, only equilibrium is x equals 0 stable. At R equals 0, we have a bifurcation point. For R is greater than 0, x equals 0 becomes unstable. 2 stable branches appear. X is plus or minus the square root of R. The stable branches are outer curves. The middle branch is unstable for R is greater than 0. Okay, and whoops, I should say, let me just write this again. This was supposed to be, let me write it on the paper here, describe. Okay, so that was supposed to be, sorry about that, describe. To save time, I'm just not going to sketch for now. I mean, you probably know how to do that pretty quickly anyway. Okay, so that takes care of number 4. Let's move along to number 5. And I apologize for how sloppy that is. Usually when I have time to write things down, I try to write more neatly, but this was quickly, I don't write quickly. I don't write well quickly. Okay. All right. Oakley dokley. So here, number 5, consider the system. dxdt is this. dy dt is this. Okay, and thank goodness they want us to convert to polar coordinates first, because that would make this a lot more manageable. So this is where we need prior knowledge of polar coordinates, and it's not too bad. X equals r cosine theta. Remember, y equals r sine theta. X squared plus y squared is r squared. So we just go ahead and substitute. Here's what we get for dx dt. Substitute. And here's what we get for dy dt. Okay. So that's just substitution. We have to be careful with our signs. And letter B. Derive equations for r dot Newton's notation and theta dot Newton's notation. So what we're going to do here for letter B, we're going to use this r dot equals x dot plus y dot over r. Use this for r dot. This helps. And what we're going to do is just compute compute the numerator first, right? X dot plus y dot, substitute. Just substitute, right? And take a look at what we get. Okay. Comes out to r squared, quantity 1 minus r squared. And if x squared plus y squared is r squared, hence r dot equals r times the quantity 1 minus r squared, right? That's simplifying that. Remember, there was a denominator r, so not bad, right? because remember we're taking the r squared, 1 minus r squared. This is the numerator. Dividing it by r, then we get r times the quantity 1 minus r squared. Okay. Second part we're going to compute. Now we have theta dot equals x times y dot minus y x dot over r squared. Do the same exact thing, substitute in, and then we're going to divide by, that's our numerator, substitute in there, and then divide by r squared. Negative r squared divided by r squared, that yields theta dot is negative 1. Okay? That takes care of letter B. Now the interesting parts of the problem. Show that a limit cycle exists. Okay, so we're dealing with a circle, circular type problem. The radial equation is r dot equals r times the quantity 1 minus r squared. That's your radial equation. Okay, and take a look. Look familiar. Equilibria. R equals 0, R equals 1. Okay? So we get our equilibria for the radial equation. Now, let's think about what would happen here for 0 is less than R is less than 1. Okay? Because we're dealing with a unit circle. Okay? R dot is greater than 0. So what happens to the trajectories? They're going to move outward. Okay? For r is greater than 1, r dot less than 0, the trajectories move inward. Thus, trajectories approach r equals 1. Therefore, the circle x squared plus y squared is 1 is a limit cycle. So that takes care of letter C. And I apologize for writing letter D like this, but I'll read it so hopefully it comes out on video where it's legible. Determine the stability here, its stability. So this is what we could say about the stability. Since the trajectories inside the circle move outward and trajectories outside move inward, the limit cycle attracts nearby trajectories. Hence, the limit cycle, the unit circle x squared plus y squared equals 1, is indeed asymptotically stable. Okay, so that's part D. We did A, B, C, and D for number 5. Okay, we can move along to number 6. And number 6 is mostly writing. Conceptual problem for number 6. Okay, and these are good. Okay, number 6. Consider a planar system with a trapping region R and exactly one equilibrium point inside R, which happens to be unstable. Okay, and state the Poincare-Bendixson theorem. Explain why a limit cycle must exist in R, and can there be more than one limit cycle? Briefly justify. Okay, so this requires, studying notes and text and stuff online to be familiar with the Poincare-Bendixson theorem. So for part A, if we're going to state that, okay, that basically says if a trajectory of a planar system remains in a closed bounded region and its W limit set contains no equilibria, then the W limit set is a periodic orbit limit cycle. Okay? All right. So from here, part B, explain why a limit cycle must exist in R. Okay, because R is trapping, trajectories remain in R forever. There's exactly one equilibrium in R, and it is unstable, so nearby trajectories cannot converge to it. Hence, some bounded trajectories have W limit sets containing no equilibria. By the Poincare-Bendixson theorem, W limit set must therefore be a periodic orbit. So at least one limit cycle exists in R, in the trapping region. Okay, so that's part B. Part C, can there be more than one limit cycle? Briefly justify, and that answer would be yes. The theorem indeed guarantees the existence of at least one periodic orbit, but it does not guarantee uniqueness. A planar system can contain multiple nested limit cycles. Okay, so that is requires knowledge of that theorem. And it's interesting questions. All right, so we're moving along. And I encourage you to, if you want, pause the video and try problems before we go over the explanations. It's up to you, though. Okay, so number 7. Okay, let's go over this for number 7. Consider x sub n plus 1 equals r x sub n, quantity 1 minus x sub n. A, find the fixed points. B, determine their stability in terms of r. 4, r equals 3.2, describe expected behavior. And D, what phenomenon occurs as r increases beyond 3. Okay, so here's A, here's B. Sorry about that. B goes up here. Here's C. Here's D. Okay, so let's go over letter A. Find the fixed points. So we take our equation, our fixed points satisfy, in this situation, remember, x sub n plus 1 equals x sub n equals x star. So we have x star equals, basically algebra from here, x star equals r x star, quantity 1 minus x star, right? X star equals r x star minus r x star squared. Okay, from here, rx star minus r x star squared minus x star equals 0. Factor out the x star. So what we could say in this situation is thus either x star equals 0 or r minus 1 minus rx star equals 0. So rx star, set that equal to r minus 1. We get x star equals r minus 1 over r, or 1 minus 1 over r. So we have fixed points are at x star equals 0 and x star equals 1 minus 1 over r. That's for our fixed points. Okay, so moving along to number 2, determine their stability in terms of r. Okay, so for a discrete map, x sub n plus 1 equals f of x sub n. A fixed point is stable if absolute value of this f prime of x star, absolute value of that is less than 1. So here f of x is this rx minus rx squared. So f prime of x, we're taking the derivative of that with respect to x, would be r minus 2rx, which is factoring out the r times the quantity 1 minus 2x. So we have a stability of x star equals 0. F prime of 0, well, that equals r. Stable if absolute value of r is less than 1. Thus, we could say x star equals 0 is stable for absolute value of r less than 1 and unstable and under any other circumstances. Unstable otherwise. Okay. Now, that was for at 0. X star at 0. Now going up here, stability of x star equals the other one, 1 minus 1 over r. So we substitute into f prime of x again. We get f prime of 1 minus r equals, and just be careful with the signs here, r times the quantity 1 minus 2, quantity 1 minus 1 over r, close parentheses, and then close parentheses again. Just doing the computation, you wind up with negative r plus 2. Okay? So winding up with that, the stability requires the absolute value of negative r plus 2 be less than 1. So if we solve this absolute value inequality, we're going to get 1 is less than r is less than 3. So what could we say here? In this situation, therefore, okay, we have, looks like it's stable, right? For x star equals 1 minus 1 over r. On the interval there for 1 is less than r is less than 3. Okay. So therefore is stable. Okay, sorry about that. I just realized I wrote is. I was looking at what that remark was. Yeah, just is. So right there is supposed to be is. Letter C. 4. 3.2. Describe expected behavior. All right, so if we have a 3.2 that's greater than 3, the non-zero fixed point loses stability, and from this we could say the logistic map undergoes a period doubling bifurcation. So thus solutions tend toward a stable period to orbit, and the sequence oscillates between the two values instead of converging to one fixed point. Okay. And now for letter D. Letter D. Okay. What phenomenon occurs as R increases beyond 3? Okay. Letter D. R increases beyond 3. Right here, as R increases beyond 3, okay, we get period 2 cycles appear, then 4, then 8. So this is a period doubling cascade, and that's just going to lead to chaos. Eventually, the dynamics become chaotic for many parameter values. So that's how you would take care of the phenomenon question in letter D. So that was number 7. Wow, we did 6. Okay, 3 more to go, it looks like. Number 8. Okay, so number 8, let's see what we have here. Consider, okay, x dot negative partial here, v dv dx, y dot negative partial dv dy, where v of xy is this. Okay, so part A, show the system is a gradient system. So let's go over what we need here. A gradient system has the form x dot or dx dt equals a negative, that's del operator times v, right? Gradient. So what we want to do here, remember that negative at the end, compute the partial derivatives. To make this, it would be better to change this into polar coordinates. Let r squared equal x squared plus y squared. Substitute r squared into here. Rewrite. And now what we could do is, after we rewrite, now we could take these derivatives. So we could say in this situation, dv dx equals 1/4 4x r squared minus x. And we're going to wind up with this x times the quantity x squared plus y squared minus 1. Okay? dv dy, that's going to be y times the quantity x squared plus y squared minus 1. So we could write this system, okay, as x dot equals negative x, quantity x squared plus y squared minus 1. Y dot equals negative y times the quantity x squared plus y squared minus 1. Okay, remember that minus, which is equal to this negative del operator times v. Therefore, what we could say, since it equals, it is a gradient system. So that shows that the system is a gradient system. All right, so for letter B, going with the equilibria, they have to satisfy x dot equals 0, y dot equals 0. So set these both equal to 0, right? So set x quantity x squared plus y squared minus 1 equal to 0, y quantity x squared plus y squared minus 1 equal to 0. And when we solve this, doing the algebra, x equals y equals 0, or x squared plus y squared equals 1. So the equilibria are 0, 0, and every single point on the unit circle, that x squared plus y squared equals 1. Okay, so that's the equilibria. Now, part C, we want to classify the equilibria using V. Okay, so what we could say here, the minima of V correspond to stable equilibria. Maxima correspond to unstable equilibria, according to V. So that's pretty much all you had to do for C. That's all you had to state, but it's based on the previous A and B steps. Okay, whoops-a-daisy, what am I saying? I didn't show the work. Let's show the work. So V in terms of R, V of R equals 1/4 R cubed, R to the 4th minus 1/2 R squared. Take the derivative. V prime is R times the quantity R squared minus 1. So we get critical points. R is 0, R is 1. Take the second derivative, 3R squared minus 1. And now this is from Calc 1. We technically plug in these values, right? For R equals 0, V double prime of 0, that gives you a -1. That's less than 0, so that means the origin is a local maximum. Unstable. At R equals 1, V double prime of 1 equals 2, that's greater than 0, so the unit circle is a set of plural minima, and they're stable. Okay. So, moving along here, that takes care of letter C. Sorry about that. And letter D, describe the global behavior of the trajectories. I wrote this at the bottom here. Let me see if we get this all in there. Set of equilibria. Okay, so this is what we could say for this, describing the global behavior of the trajectories. Down here, using polar coordinates, r dot equals r minus r cubed equals r times the quantity 1 minus r squared. What we could say is if on this domain from 0 is less than r is less than 1, then r dot is greater than 0. So the trajectories move outward. If r is greater than 1, then r dot is less than 0. So the trajectories move inward. So we could say, therefore, all non-zero trajectories approach the unit circle. So the origin is unstable and the unit circle is a globally attracting set of equilibria, plural, except from the origin. So I just wanted to read that. Hopefully that's legible. And that takes care of number 8. Okay, number 9. Okay, so number 9, consider this. X dot equals y dot equals x squared. Part A, show that the origin is non-hyperbolic. Okay, so let's see what we can do here. For part A, if we want to do this, we want to linearize at 0, 0 in this situation, because that's the origin. Okay, we want to get the Jacobian. Okay, I skipped some steps. Jacobians from previous problems too. So the Jacobian here would be 0, 1, 2x, 0. Evaluating at the origin, you get 0, 1, 0, 0. Okay, so we want the characteristic polynomial, and that's going to be, in this situation, lambda squared is 0. So our eigenvalues are going to wind up being lambda 1 equals lambda 2 equals 0 after you perform the computation. And now what we could conclude is, since the eigenvalues have 0 real part, the origin is non-hyperbolic. 0 real part, origin is non-hyperbolic. Okay? For letter B, find the center manifold up to the second order. Okay, so assume the center manifold. This is what we'll do. We'll assume the center manifold has form y equals h of x equals ax squared plus bx cubed plus the bcx to the 4th, on and on and on. With h of 0 equals 0, h prime of 0 equals 0. Okay, with those conditions on the manifold. Okay, so what we could say here, if we were going to take the derivative, y dot, that would equal h prime of x times x dot. Okay, now going up here, since x dot equals y equals h of x, and y dot equals x squared, right, from what we had up here, the invariance equation will yield h prime of x times h of x equals x squared. So what we're going to do here is we're going to substitute h of x equals ax squared plus bx cubed plus wbcx4, etc. So then we could say h prime of x equals, take the derivatives of these, 2ax plus 3b x squared plus dot dot dot, etc. Now multiplying, taking the product of h prime of x and h of x, we have quantity 2ax plus 3bx squared times ax squared plus bx cubed plus dot dot dot. Okay. So, in this situation, so we find the center manifold up to the second order, right? Second order. The lowest order term, 2a squared x cubed plus dot dot dot. So here we go, lowest order term. Now this is important as a note here. Not as a note, well, this is technically, we need this for part B. However, the right side is x squared, right? The right side is x squared. No quadratic approximation can match an x squared term. Thus, the center manifold is tangent to the x-axis and begins at higher order, right? Up to second order, y equals 0 plus, and then we have the terms of order here, x cubed or higher. So terms of order, x cubed or higher here. That takes care of part B. Part C, describe the reduced dynamics, what we could say here. On the center manifold, y approximates 0. Then x dot equals y approximates 0. So reduced dynamics are extremely slow near the origin. Higher order effects dominate. So what we could say here is in relation to this, the reduced equation, x dot, right, and terms of order x cubed or higher. Right there. Okay, reduced equation. And for part D, determine the stability of the origin since y dot equals x squared and we have greater than or equal to 0. The y component is always increasing unless x equals 0. Okay, so the trajectories, what we could say, drift upward and away from the origin. So in regards to stability there, so the origin is unstable. Okay. All right. So that's 1 through 9. One more to go, and these are general responses. Okay. Okay, number 10 are general responses written out. Okay, general responses 10A. What is structural stability? Okay, so, and this is for a dynamical system. A dynamical system is structurally stable if its qualitative behavior does not change under sufficiently small perturbations of the system. Examples of preserved behavior include the number, type of equilibria, stability, and phase portrait structure. So these are more of conceptual understanding, textbook, reliance on textbook definitions, whatnot, notes. Okay, this is very standard stuff. Standard in terms of this is what is expected in a dynamical systems class to be understood and whatnot towards the end. Letter B, what distinguishes a limit from a center? Okay, so for letter B, a limit cycle is an isolated periodic orbit. Nearby trajectories either approach it, stable, move away, unstable, or do both, semi-stable. A center consists of infinitely many nearby closed orbits surrounding an equilibrium point. Centers are not isolated and are not structurally stable. Okay, so that's letter B. Letter C, super important. Why are eigenvalues important in linear systems? I mean, all these questions are important, but this one, very, very important to know. Eigenvalues determine stability, growth decay rates, oscillations, phase portrait type. Examples include negative real parts, stable, positive real parts, unstable, imaginary eigenvalues, oscillatory behavior. So all of these are important. I shouldn't say one is more important than the other, but eigenvalues, you see that a whole lot. Okay, number 4, what is a homoclinic orbit? A homoclinic orbit is a trajectory that leaves an equilibrium and later returns to the same equilibrium as t approaches plus or minus infinity. Okay, and what that does, it connects a saddle point to itself. Okay, another textbook type question. And last one, give an example of a bifurcation other than pitchfork. Okay, so there are other examples. So examples include saddle node bifurcation, transcritical bifurcation, and the hop bifurcation. So in this case, the hop bifurcation where an equilibrium changes stability and a limit cycle is created. Okay, so those are some terms to go over, whatnot. So that's it. So that was a practice final exam for dynamical systems. Hopefully this could help you review for exam or just review in general. And thank you very much and have a great day.